Okay, let's start with, this may be quite a while in the past, so let me go over question 1 from the last midterm. It said if you have a probability density of the form Pxyz equals C sine of this expression, it was something like 2x squared plus 3y squared plus 4z squared. And it was on the region, it was the first octant, as well as you take that square root and you say it's less than or equal to pi. So then the question was to find C. And so just to remind you about what kinds of things these involve, there really are 2 steps here. One, you have to rescale. And that just basically means you get rid of the 2, the 3, and the 4. And so once you do that, that probability density becomes the spherical coordinate radius. So this is u squared, v squared, and w squared. And then the region, of course, is still the first octant. And that, of course, just means, let me just, you know what I mean. It's like the first quadrant. And our rho will be less than pi. Okay, so then the problem becomes a matter of using spherical coordinates to do integration. So the only question is, how does the integral transform? So when you take a triple integral over various limits and you have some function, you need the Jacobian, because then this thing, dv, it'll be equal to the Jacobian times du dv dw. So the Jacobian, of course, is just, this shorthand notation, because there's cancellation of the denominator with the numerator, formally speaking. And of course, this is just this determinant. And so on. And the nice thing about this change of variables, of course, is that it's just diagonal. So I think if you solve for the x's and the u's and the v, x's, y's, and z's, I think you just get x equals u divided by square root of 2, y equals v over square root of 3, and z equals w over square root of 4. So you end up with everything 0 except for the diagonals, because xv is 0, for example. So you end up with 1 over square root of 2, 0, 0, 0, 1 over square root of 3, 0, 0, 0, 1 half. So that determinant evaluates out nicely. So you end up with, once you change variables, so it's now a triple integral over new limits. So then it's f of rescaled variables. And then it's times 1 over 2 root 6 du dv dw. So this was, I think, the main challenge of this problem, because once you do this, now it's just use spherical coordinates. And just to set up what the integrand looks like, the new limits are just rho between 0 and pi, in order to get that first octant, what we do is we just say, well, I would just draw a ZR plane, and I would draw a YX plane. And in order to get that first octant, we need theta to range from 0 to pi over 2, and we need phi to range from 0 to pi over 2. So these two ranges give us that first octant. So therefore, our new limits, you'll just get let's see, yeah, you'll just get pi over 2, and pi. And so our f is just p. Yeah, our f is just p, so it'll just look like sine. So c sine rho. And finally, our dv times our Jacobian, 1 over 2 root 6, this will look like rho squared sine phi d rho d phi d theta. And then you have that 1 over 2 root 6. And so, yeah, so this looks a little messy, but actually this is a pretty easy integral to evaluate because, of course, it splits. And the reason, just to refresh your memory, the reason it splits is because the integration limits are constant. So it's just it's a rectangle in spherical coordinates. And so you can split integrals of this form, f of x g of y. So when you split that, it looks like 0 to pi over 2, 0 to pi over 2 sine phi d phi. And finally, we have that rho integral where c of c sine rho, rho squared d rho, and you also have the silly square root of 6 factor. So now these integrals are totally doable. So I think the real challenge was this rescaling business. So if there aren't any questions, I'll just move on to the second problem. So the second problem was to find the mass of a laminate plate. And what that means is just it's a 2D object. Given by the region x plus y less than or equal to 2, with density rho equals e to the 2x. Okay, so really, I think if you draw what this actually is, that helps a lot. It turns out this is just a diamond. So, and how do you do that? Well, you can split this up into cases if you like. So if you do x greater than 0, y greater than 0, then this is just x plus y less than 2. If you do x less than 0, y greater than 0, then to make that negative x positive, we stick a minus in front of it. Because remember, absolute value is positive. And similarly, there's going to be an x greater than 0, y less than 0 case, where you'll have an x minus y. And finally, you'll have an x less than 0, y less than 0 case, where everything is negative. And so it turns out you had diamonds. For example, what you do is you just solve for y. And then it becomes a little clearer what's going on. Okay, so we have to integrate over this diamond. And the trick you have to do is you have to, well, okay, you can do it two ways. I think the hard way is piecewise and just do nothing. You don't need to do a change of variables if you do it piecewise. But when I saw people doing this on the exam, I think a lot of them make mistakes. So I think this is a much harder way. Like, you know what I mean, right? When I say piecewise, I say, like, if I call this 2, 1, 3, and 4, then you can do an integral of something like this. X will range, of course, from -1. What is this? This is 2 and -2. X will range from -2 to 2, and then your y's, it'll just range from, well, it's a piecewise curve, so we have to split the x's first, right? So your integral from -2 to 2, it actually goes to 2 integrals, -2 to 0, and 0 to 2. And then what'll be on the inside, the dy's? Well, first you'll have an integral from 3 to 2, and then, so there'll be your dy's, and then you'll have your integral from 4 to 1. So you'll have to evaluate essentially two separate integrals in order to do this problem, and it just gets kind of messy. And so another way to do that is just to rotate. And that is basically you just transform your diamond to a square. And this will be given by new variables u and v. And so how do you find u and v? You actually just use the equations you're given. Right? Like, notice how we just have essentially copies of x plus y and x minus y everywhere. Right, you can, well, yeah, we can use this one. So here's x plus y, here's negative x plus y. And then this one, of course, is negative x plus y. And then finally, we have negative x plus y. Right, so we see that x plus y and negative x plus y, these are natural choices for our u and v. And I think, yeah, why not? Let's just do u equals x plus y and v equals negative x plus y. So in order to get the new limits, you just plug u and v into the edges. So remember, the edges are just, you make these equals. So the first edge is x plus y equals 2. The second edge is negative x plus y equals 2. The third edge is x minus y equals 2. The fourth edge is negative x minus y equals 2. So if we plug in u and v, we just get u equals 2. We get v equals 2. We get, let's see, negative v equals 2. And we finally get negative u equals 2. So this is, of course, just v equals -2, u equals -2. So these are our integration limits that we'll use. Okay, and the final thing we'll need is that Jacobian. This will allow us to integrate u and v. So the Jacobian, of course, we write that shorthand notation. We know there's just a determinant. So xu, xv, yu, yv. So if we just do these, we can solve for x and y up here. If you could do that, or you could save a step and just flip it. Because this is like saying that u dx is 1 over dx du. So these derivatives are easy. Ux is 1, uy is 1, vx is -1, vy is 1. I'm sorry, it's 1 over this. So you just need to add a 1/2 to the integrand, and then you'll have the correct integral. So 1/2 du dv, that's our dA. So now we just have our limits. Our limits will go from, I think it's just -2 to 2, right? So -2 to 2, -2 to 2, and all right, now we just need our integrand. Our integrand was rho, I think, because we're just looking for the mass. So we just have rho equals e to the 2x. So now I'm just going to rewrite in new variables. Let's remember that, I guess we have to solve for x, so that's where we have to do that. How would I do this? I would just subtract the equations. So u minus v is equal to 2x. So this is e to the 2 times u minus v divided by 2, so it's e to the u minus v. So that's nice because it allows you can split it. And you have that divided by 2 because of the Jacobian. And so these are easy. And so notice that there's no piecewise integration that's happening now. It's just simple products of 1D integrals. So the rotation, it always makes things nicer. It's just you have to go through a little bit of rigmarole. I think the drawing is always useful. Okay, if that's all, what I'll do is go to the next question. And I will not, the next question I thought was a little easy. I think almost everybody got this question, right? Finding the volume of the sphere in cylindrical coordinates. And so I won't go over that. What I'll do is I'll go over the first question of the second midterm. So if we let f equal r squared, what was it? It was r squared k plus pz r, and then k is the usual unit vector in the z direction, r is the usual x, y, z position vector, and p is just a constant. Then the question was to compute the divergence of f and the curl of f, and to find p when that equals 0 and that equals 0. And it'll be different p's. So with this question, what you have to do is I would rewrite this in a component form. with the angle brackets. So the fact is that r squared k is actually equal to 0 if you distribute. It's actually equal to 0, 0, r squared, because there's just a 1 for this k. And similarly, PZR, you just distribute the PZ inside. So you get PZX, PZY, and PZ squared. So you end up with F equals this thing, which is PZX, PZY, and what is this? This is R squared plus PZ squared. Okay, so we now have to use the usual definitions of divergence and curl to compute this thing. So listen, the divergence is always easy. You put the x with the x, the y with the y, and the z with the z. So this just reduces to pz plus pz plus, what is this? This is, remember, r squared is x squared plus y squared plus z squared. I forgot to mention that. So really there's 2 of the z squares that'll contribute. So you'll have a 2z plus a 2pz. So you end up with something like 2 plus, what is this? This looks like, oh, it's 2p plus 4. No, what is this? This is a 2p. This is a 2p, so we end up with a 4p, and then plus 2. 4p plus 2 times z. Okay, so this is equal to 0 if p is negative 1/2. And so we won't actually get p equals negative 1/2 for the curl. We'll get something else, depending on what the curl looks like. So now we have to compute the curl. And if I just rewrite what f is really quickly, then we can compute the curl. Remember, you can always think of the del as a vector, and we're doing a cross product. So you have I, j, k. And so our curl is just evaluating this determinant. So first we get 0. Remember, the x derivative of that first term is clearly 0. And then minus, we'll actually get another 0, right? Oh, what am I doing? I just did the zth component. Okay, so I times, you select the I, you take the determinant of the other columns and rows. So you end up with pz squared plus r squared minus zth derivative of pzy. So really, what is this? This is just, I think you just select this r squared, right? So it's just a 2y minus, what is this? This is py? So you end up with, you have to add the minus sign, right? Because it's a determinant. So if you select the j, then you need to select the I and k columns to do your determinant with. So it'll look like ddx of pz squared plus r squared minus partial derivative in z of pzx. So I think this is just 2x minus px. It's pretty much the same thing as the y, right? So then finally we have that plus k, and I think I did that before. That was 0, right? Because x applied to y is 0, y applied to x is 0. So we end up with just, what is this? This is 2 minus p, and then we have p minus 2 if you account for that minus sign. Oh, I'm sorry, that's an x. So I think it's helpful to factor out that p. term. So we get p minus 2 times negative y positive x. So clearly, it's equal to 0 when p equals 2. And by the way, if it's worth noting, if we ended up computing something like this, px and y, I would actually conclude the curl is non-zero for all. Well, I would say it's not identically 0. It's non-zero for all p, because if I chose p equals 0, we would get 0, y, 0. And so there's always, you can just choose y equals 1 and you get a non-zero curl. So as a vector field, it's non-zero. You could also just say p equals 0 and y equals 0 gives a 0 curl vector at a point, if you just specify that more precisely at a point. But yeah, but clearly this scenario is much nicer. There's no ambiguity there. So the last problem I want to mention is the chain rule problem. So the chain rule problem is if you have a function u equals u of x, y, and you have polar coordinates x equals r cosine theta and y equals r sine theta, the question is to find u theta theta. And we know that u theta theta is just shorthand notation for the second derivative in theta, or you apply 2 theta derivatives to a function. This problem is a little messy, but if you just follow the usual procedure, then it's just mechanical, and you just have to the whole thing just boils down to bookkeeping. And because this is one of the more useful concepts from this class, I probably will include something like this on the final. So I think it's worth going over. So how do you do this? Well, let's just start with u theta. And so remember, if we do 1D, if I were just doing u, and you just had one function, then how would I do u theta? It would just do ux times x theta. So it's going to be very similar in 2D, but you just now have to deal with x and y. So just like in 1D, it's ux times x theta. But now you also have to do uy times y theta. And this reflects the fact that u is a function of x and y. So x theta is just minus r sine theta plus r cosine theta uy. And because I'm the laziest person on the planet, I'm going to say rs plus rc, as if u sub y is not already lazy enough. So now we have u theta, and this formula is going to be crucial because we'll be using it again. Because actually, it'll be helpful to evaluate u theta x and u theta y. So first of all, let's just take the second derivative of u theta. So it's the theta derivative of this expression. So there's going to be 2 terms from the product rule. So that first term, let me just split it into theta stuff and non-theta stuff. So first we have the theta stuff. So you differentiate all the theta things. So you have partial theta of minus s. Then you have the theta derivative of rcuy. And then finally, you have the non-theta stuff, which is minus RS. Let's see, it was theta derivative of ux, and then you have the RC times partial derivative in theta of uy. So we just have to unpack these four terms, and really that's what's going on with this problem. Okay, let me not make technology more complicated than it has to be. So I'm just going to rewrite this. Okay, partial theta u theta equals this stuff. So this is all the theta stuff. And then finally we have the non-theta stuff, which looks like minus RS theta derivative of ux plus RC theta derivative of uy. So now you go back to our formula here, because this actually gives us a recipe for computing any theta derivative. So to get these things, you're just going to plug ux into that formula. Replace u with ux. So in other words, u will replace with ux. And we'll do the same thing with uy. Okay, so let's just recopy that formula down. So if I do ux theta, I should get something like minus rs uxx plus rc uxy. Because all I literally did was just replace u with ux. And we do the same thing with uy. And we get these things. So now we just plug these all back in. And of course, the theta derivative of sine is just cosine. So we'll get minus r c ux plus, or rather this will be minus, right, because the theta derivative of cosine is just minus sine. So it'll be minus rs uy. And then finally, we'll have all of this nastiness, which we just have to plug in verbatim. And then finally, we'll have minus rsuxy plus rcuyy. So I think the last step, we just need to expand this thing. So the first terms are the same. So now we'll have plus, looks like this is plus r squared s squared minus r squared sc. And then we'll have minus r squared cs. Finally, we'll have plus r squared c squared uyy. So let's just combine everything. So we'll have the first two terms plus r squared s squared uxx, and then finally the whole point is we have this minus 2 r squared sc uxy, and then finally plus r squared c squared uyy. So let's see, what's the hardest part of the problem that you might want to focus on if you were studying this? I think knowing this trick, this is pretty useful, and the substitution trick. And you also want to deal with the product rule. So the product rule and the substitution are probably the hardest parts of this problem. The rest is just bookkeeping and algebra.